Hello everybody, welcome back to a new video. This week we're going to be starting a new module. The new module is going to be focused on mechanical and electrical systems. This module is going to be divided into 3 weeks, just like the last module, because there's a lot of stuff that we need to get through. This week we're going to be focusing on HVAC. Next week we'll be focusing on electrical, and then 2 weeks from now we'll be focusing on plumbing systems. For the reading this week, you need to be looking at the mechanical and electrical systems reading that I will have posted to Blackboard. And you only need to read pages 1 through 8 of that. And then also in your textbook, chapters 12 through 14. The module is mainly going to focus on what is within the reading here that I have posted to Blackboard. That reading just really summarizes everything in a really good way. The textbook goes into a lot more detail, and they talk about a lot more specific topics, but in terms of what we need to know, we really don't have to go that in depth on it, because a lot of the information you're probably not really going to use all that much, or you'll never need to really recall it. Really, this reading that I have here kind of boils everything down to its essence of the main points that you really need to understand. So I think it's going to be in our best interest to just focus on this reading and then use the textbook more as a supplement. But I'm going to be pulling some content from both of them for the quizzes and exams. All right, so make sure you are reading both the textbook for the module, the chapters. I think in total is going to be about 80 pages of reading, and then this reading is going to be probably somewhere around 20 pages total. So over the next 3 weeks, you're looking at maybe 100 pages of reading total, but just try to get through it and grasp it the best that you can. All right, so let's get started here. Like I said, we're going to be talking about HVAC. So mechanical systems that interior designers should be familiar with include heating, cooling, plumbing, and fire protection. Electrical systems include power, lighting, telephone, and other communication systems. Interior designers are not directly responsible for specifying components of these systems, but they must be familiar with them to effectively coordinate with engineers. They must also often make design decisions that are directly related to these systems. All right, so for example, let's say we have a soil stack or some other piece of mechanical equipment, and it's existing in a building, and we might want to move it for one reason or another. We should have an understanding of what that soil stack is there for, why it is in the position it's in, so that we can understand if it is possible to be moved, and also who we would need to coordinate with to determine if it can be moved. All right, there's going to be a lot of code requirements associated with mechanical equipment, so we just have to have an understanding of it, so that we can work around it when it comes to incorporating our design intent on a project. All right, so start here with HVAC. So HVAC is an acronym that stands for heating, ventilation, and air conditioning. The heating, ventilation, air conditioning can be combined into a single system, or they may exist as separate systems within a building. So you might have one system that's specifically for heating, and then you might have another system that is specifically for cooling. They might not be integrated together. It just really depends on the type of building that you're working with. So there are a few different types of HVAC systems, and they are classified by the mediums that they use to heat or cool the building. So the two primary mediums are air and water, and some systems may also use electric or electrical panels, or they may even use a combination of the different media. Okay, so some might use air and water together, or they might use air and electrical together. It just depends. An all-air system, so these are systems that cool or heat spaces by conditioned heat alone. Heat is transported to the space with supply and return air ducts. And a common example of this is a residential forced hot air furnace. So basically how this is going to work is a boiler powered by oil or gas is going to heat the air, which then is distributed throughout the house with ductwork. The air is then returned to the furnace through vents for reheating. All right, so here I have a little diagram, and this is showing a typical gas-powered heater, so like a furnace unit. All right, and this just walks you through kind of the process of how the air is taken and heated. Basically, the air is brought in through a blower, and then it runs through the main portion of the furnace system here, and we have our gas lines coming in, and we have a flame that's being ignited here, which actually is heating up the air that's within these chambers. Okay, and then as the air is heated up, it is then exhausted out the top here through what is known as the plenum. Okay, so the air that's actually coming out of the furnace system, this is our supply air. Okay, so the air is being supplied to the space from the heater. It has just been heated, or I'm sorry, from the furnace. And then after it enters the different spaces of the building, it will naturally cool down, and then it will return to the unit here, the furnace, through special ducts that are called return ducts. Okay, and then the air is it's basically a circular pattern, so then it's recirculated back into the system and reheated, and then it's sent back out through the plenum again to reheat the spaces. Okay, here is a diagram that's showing basically the distribution system within a house. So this is what you're typically going to see. So what we just looked at on the last slide, that furnace, that's basically this unit down here that you're seeing. What we're looking at right here, this is like an electrical control panel, and this is tied to all the thermostats that are running throughout the house. So you can see we have 3 different thermostats here, and they're all in different zones. Okay, so we have one like out here in the garage, one on the living room area, and then one up here like in the bedroom. So these thermostats are all set to specific temperatures, and they are basically telling this panel to provide, they're telling this panel to tell the furnace to provide air to specific zones of the house. So you can see we have these different ducts here. So we have a duct run right here, and then there's a second one here and a third one here, and these are all going to the different zones, right? So this first one is going to this zone right here, the thermometer 1 zone. The second one is going to the thermometer 2 zone here on the second floor, and the third one is going to the thermometer 3 zone here. All right, so if you're standing in the garage, for example, and you want to turn up the heat, you're just going to go to the thermometer and then put in the temperature that you want the room to be set to. And then once you do that, that's going to send the electrical signal here to your control panel. And then the control panel is going to tell the furnace to send out temperature, that is the heat that you selected, through this third duct line here into the garage. Okay, so a typical system like this, they're divided into individual zones so that you can individually heat certain zones of the building independent of one another. So these 3 duct lines that I just talked about, these are our supply lines. Okay, so you can see the supply lines are illustrated by the red red arrows that are coming out of these registers in the different spaces. And like I said, that is the air that has been heated that's coming directly from the furnace. And then if you look here, we have a separate duct system, and this is our return duct system, okay? So what's happening here is all of the air that has been distributed through the supply ducts within the building then are attracted, or they're being pulled in to the return duct system, okay? So that all that hot air, as it cools down, it's being pulled into that return duct from all the spaces, okay, indicated by the blue arrows, and then that is going to be drawn back into the system here for reheating, okay? So like I said, it's a circular system, okay? So it goes up here, it goes out, gets pulled back into the return duct, and then comes back into the system, gets reheated again, then gets redistributed. Here we have an example of a central air conditioner. All right, so an air conditioner is basically a separate unit that is tied into the HVAC system of the building. So this is a typical scenario that basically you would see like in a residential situation. So we have our furnace here, like I showed you on the last slide, but then on the exterior we have a air conditioning unit that sits there. And I'm sure all you guys have seen these before outside of your houses. But basically this unit here uses condensation, so it produces condensation through the components that are within it, and then the condensation or the vapor that's produced gets brought inside through these lines that we have here, and then the air or the furnace is going to be drawing in warm air from the house, and that warm air is going to be moving past these coils, which are being refrigerated. Okay, so basically these coils here are being cooled down by the air conditioning unit on the outside, and as the warm air coming in passes through them, it's being cooled down and then distributed throughout the house. And then that circular system is still in play with an air conditioning system. It's just that the air is cooler, right? But this air conditioning unit is going to tie directly into the existing ductwork, and it's going to use the same exact ductwork as the heating system. Air conditioning units usually connected to the same ductwork to provide cooled and dehumidified air. In commercial buildings, we have several variations of systems such as variable air volume, high velocity dual duct, and constant volume with reheat, and also multi-zone systems, okay? So just be familiar with this terminology. You don't really necessarily know what all these are, but you might hear them come up down the road. So here you heard them first. This is some of the common systems you'll run into. Every all-air system requires air supply ductwork, registers, and return air grills in all spaces. In commercial buildings, fire dampers are required in locations where ductwork penetrates fire-rated wall assemblies. All right, so we've talked a little bit in the past about fire-rated wall assemblies, but basically anytime you insert some sort of a penetration that is breaking the assembly, you're going to have to incorporate special components or special design considerations, maybe is a better way to say it, to address that penetration, okay? Basically, any penetration that you're inserting is going to create like a weak spot in the firewall that's preventing the fire from spreading through the building. So you're going to have to compensate for that with special design considerations, okay? And with a HVAC system that is penetrating that fire-rated wall, we do that through the use of fire dampers. Okay, so fire dampers, these are devices that will automatically close to block off the flow of fire through a building when a fire is being detected by the system. So here's a little video that explains how these fire dampers work. I'm actually going to play it here just because it's really short and it explains a lot better than I can just by talking. All right, so here you can see a fire has started in a building, and then it's going to want to travel up through that ductwork there. As it passes through the ductwork, it's going to want to go through this damper, which is the system here with the fins. And as that heat passes through the system, it's going to trip a breaker or trip a fuse. And when that fuse is tripped, it's going to cause the damper to close the fins and block the fire off from moving further throughout the building. All right, next we have all water systems. So with all water systems, water is heated within a gas or oil powered boiler unit, and it is then distributed to spaces through a series of pipes. Heat is transferred to the air then through radiation. All right, so here we have a few examples of these all water systems. So first is sort of like a classic version of an all water system, and this is a radiator. Okay, so you see this in a lot of older buildings. Basically the water is going to come through a supply line here. It's going to run through these coils, and the water's already heated, but it's going to be running through these coils then, and then as it runs through these coils, it's going to be radiated into the air. So any air that's passing through this is going to be heated up, and then it's going to radiate throughout the space, okay? And then once it is all the way through all the coils, it then returns to the heating system, to the boiler, through the line here on the other side, okay? This here is a baseboard radiator. It works much in the same way, except this is sort of just a different form factor. And then here we have an example of a radiant floor heating installation. This is one that I actually saw a few weeks ago when I was out shopping. So I was at this old shoe store, basically in Amish country, and down in the basement they had clearance items. And when I was down there, I looked up and I noticed that they had a radiant floor heating system installed. And I knew that we were going to be talking about this in a few weeks in the class, so I just decided to take a few pictures of it because I thought it was really interesting seeing how they had one installed. I'd never really seen one in person like this, but basically you can see they just have a series of, this is called PEX tubing. Okay, we'll talk about that more when we get to plumbing. Basically, they're just plastic water lines, and they are snaked back and forth in a serpentine pattern on the underside of the subfloor here between the joist bays. These joists that we're seeing here, you should recognize these from the last module. So these are I-joists. These are engineered I-joists, okay, that have a OSB middle to them between a top and bottom chord. All right, so those are those engineered components that we talked about in the past. But the system that you see here, like I said, this is a radiant system. So as the water is traveling through these lines, it is being transferred, the heat from it's being transferred to the subfloor, and it is then radiating into the space above it. Here's a diagram of what's called a hydronic distribution system. So this is just a fancy word for basically what we've been talking about, these all water systems. So compared to the air system, we don't have ducts in this system, right? The ducts are all replaced by a series of pipes. Okay, so these goldish brown colored things are a series of pipes that the water is running through. So the water is being heated within a boiler. All right, here's a boiler system. Or it can be heated also in a special water heater tank. And then once the water is heated, it is then distributed through the pipes to either the radiator. So this could be like a regular old radiator like we saw on the last slide, like this, or it could be a baseboard radiator. And then the air is around it is then heated, and the heat is just radiated throughout the space, okay? And then just like the air system, it's very similar in its control scheme, where we have thermometers that are being tied to a control panel. which is telling the boiler unit or the water heater the temperature that the room should be so that it can heat the water to the appropriate temperature and then distribute it to the room where the air is then heated. Okay. Oh, and also with the thermometers, how those work. Basically, once the air in the room hits the correct temperature, they will basically trip and tell the unit to shut off, okay? This slide here is showing an example diagram of basically what I was talking about a couple slides ago when I was discussing the radiant in-floor heating system. So just like the hydronic system we talked about on the last slide, the setup for the radiant heating system is very similar in terms of the mechanical equipment required down here in the basement. So you can see we have our water boiler, and then we also have our electrical control panel, and then also the thermometers as well. And they're distributing the water through a series of pipes or tubes, just like the last example. However, once they reach the rooms up here, they're not being distributed to a unit, I guess, like the radiator or the baseboard heater. They're instead being distributed to the series of pipes, which are laid out in a serpentine pattern. And as these pipes heat up with the warm water, they're going to be radiating that heat inside of them to the subfloor and then all the way up through into the air above. Okay. Right here is a video that explains hydronic heating. So basically it just talks about these heating systems that utilize water, and this is a really interesting video to watch. So now we're going to talk about other systems. So there's also a thing called combination systems, and these use ductwork for supplying fresh air, but then they also use water to heat or cool the air before it's introduced into the conditioned space. These are called terminal reheat systems. There are also other installations that use an all-water system for heating and a separate duct system for ventilation and cooling. Okay, so you might see some buildings that use a combination of the two. So they might use water for one thing and then air for another thing. It just depends. So now we're going to talk about system requirements. So there's several things that an interior designer should understand about HVAC systems in order to make informed decisions regarding space planning, ceiling design, and layout and remodeling. So space for ducts, pipes, and mixing boxes. Ducts and plumbing pipes are usually run between floor joists in residential construction. All right, so if you think back to when we were talking about the structural systems, we have our series of flooring joists, and we have bays between those. That's known as our plenum space, and between those joists, that's where you're going to be running all of your mechanical equipment, so your plumbing, your electrical, and your ductwork. Right, that's all going to be running between the joists. Sometimes horizontal ductwork must be run below the floor joist, though, and in these situations, they might need to be concealed with an enclosure, such as a soffit. Right, so a soffit, basically, if you're not familiar with the term, this is the best way to describe it, it's a furred out portion of wall that is enclosing something, so it's covering something over. So if you look at this image down here, you can see we have framing that's being built around this ductwork here, and then once it is finished off with drywall, this is what it looks like afterward. So there are just situations where you might not be able to run those ducts within the joist bays, and you might need to drop it down below. And in those cases, you might have to build out some sort of an enclosure like this to cover over that ductwork, okay? In commercial construction, horizontal ducts are run through plenum spaces, and vertical ducts are run through chases. Chases are vertical shafts, usually between walls, that provide spaces for mechanical equipment to run vertically through a building. Right? So when you hear the term chase, basically a good way to think about this is like a chimney that pipes and equipment is running through. Right? It's just an open space that runs all the way through the vertical layers of a building. or through the levels of a building, I guess would be a better way to say that. And it's just wide open, and you have all of your mechanical equipment within there, so that it can be distributed through all the layers or through all the levels of the building. The locations of mechanical equipment can impact the design elements, such as lighting fixtures. In some cases, ductwork may make it impossible to recess lighting fixtures into the ceiling. Often, interior designers need to work around complications created by mechanical systems within a building. Right? So you're going to have to be conscious of the way these mechanical systems are being implemented into buildings, because the work that you're going to be doing as an interior designer is going to be directly related to it. So you're not going to be the one specifying the mechanical equipment and how it goes into the building, but you will be specifying things that are going to be in close contact to that mechanical equipment. So it's important for you to understand sort of the layout and how the mechanical equipment is put into the building, so that you can coordinate with the engineers who are designing the mechanical equipment in order to make your design as best as it can be. Okay, because you're gonna have to be working around that. Like, for example, like this is saying, maybe you're working on a lighting layout for a space and you want to incorporate some recessed can lighting. But if there's ductwork directly above the ceiling where you're trying to do that, obviously that's not going to work. So you might have to sort of shift your approach for the design and incorporate some other type of a fixture. Okay, maybe it has to be a fixture that is suspended below the surface of the ceiling. You know, what you initially wanted to do just might not be a possibility. So it's going to be important for you to understand some of those complications that you're going to run into, because they do happen quite a bit. Okay. Mixing boxes, these are devices that are located within the plenum spaces, and these adjust the quantity or temperature of air that's going into a space from the main supply lines. They also reduce the velocity of air, and they attenuate noise. Okay. So access. All right, so building codes require that access be provided to certain components of mechanical and electrical systems. Access must be provided for components such as valves, fire dampers, heating coils, mechanical equipment, electrical junction boxes, and communication junction boxes, and similar devices. All right, so basically you have to build into your design ways for people to access the mechanical equipment, because very often things break down and you have to do maintenance on them. So they have to have some way to get to these things. They can't all just be enclosed and, boxed around with no way to access them. So if components are located above acoustic ceiling tile, ACT ceilings, access is provided simply by removing the ceiling tile. So if you ever see an ACT ceiling grid system, you just pop those ceiling tiles out of their grid, and you'll have full access to all the equipment that is above the ceiling. In other locations, such as inside a wall, you may have to install special access doors. So usually these are doors that are made of steel or some other type of metal, and using these may come with special fire rating requirements. Again, like I said previously, whenever you're creating some sort of a penetration inside of a fire rated assembly, you're going to have to incorporate, some component that sort of addresses that penetration and doesn't weaken the overall integrity of the fire rating system that is within that wall. Okay, so you're basically introducing a vulnerability into the fire protection system, and you have to then basically undo what you did by using like a special sealant around the outside of the door. There's all kinds of things required by code that you're going to have to incorporate to get that fire rating back up to where it was prior to adding in the penetration. All right, thermostats. So the location of thermostats is usually determined by mechanical engineers. These are installed in locations that are away from exterior walls, heat sources, and other areas that may adversely affect their operation. So obviously a thermostat works by measuring the air temperature around it, and it then tells the heating system or HVAC system what temperature the space needs to be. But if it's in an area, say it's close to a window and there's like a draft or something that is cooling the airspace that's directly around that thermostat, that's not going to be providing a very accurate reading to the HVAC system, okay? So basically you want to put the thermostat in an area that is getting a good average overall temperature of the entire space, and not in an area where there's a concentrated warm spot or cold spot, because then you're just going to be having issues with the operation of the HVAC system, okay? Normally they are placed 48 inches above the floor, but the mounting height should be coordinated with light switches and other wall-mounted control devices for a uniform look. Coordination with other ceiling items. Interior designers often need to coordinate the locations of air supply diffusers and return air grills with other ceiling items such as lights, sprinkler heads, smoke detectors, speakers, and other related components to make the ceiling as functional and as well planned as possible. Interior designers need to work closely with mechanical engineers to ensure the desired types and locations of supply and return devices do not adversely affect the operation of the HVAC system. Okay. Window coverings. So as an interior designer, you're often going to be specifying window coverings and treatments for windows inside the building. But these can interfere with the heating and air conditioning loads within spaces if air supply diffusers or heating units are placed near windows, okay? So that's something you have to be conscious of. In commercial construction, interior designers need to know, or they need to consult with architects and engineers to ensure that window coverings they select will not negatively affect the HVAC system. Okay, so here we have a diagram from the reading, and this is basically showing you your minimum clearances for window treatments. So if we have a window here, okay, and then we have our heating and cooling supply system here. So let's say this is a heating system that's running along the wall. Maybe you've seen those if you're like, I know my high school had those around the perimeter heating system where it pushes out the warm air. If you have something like that and you have your window covering here, you have to meet minimum clearances between the top of that heating system and the bottom of the window treatment, and also all the way around as well. So on the top and then on the back side between the treatment and the window itself. And this is in place to prevent this treatment from interfering with the operation of that heating cooling system, okay? If it does not meet that clearance, then it's going to start interfering with how that air is being pushed into the space, right? If that was too low, it might block off the airflow. So you have to make sure that you meet the minimum requirement for how those are being installed near these systems if they're, for example, like at the perimeter of the space. Air supply options. So many types of air supply diffusers are available depending on the requirements of the HVAC system, the type of wall or ceiling in which they are mounted, and the appearance that is desired. Okay, so these might be specified by the engineer, but you will also have input in terms of the design, and if there are like specific, like if there's a specific look you're going for. So it's going to be common to see 1 foot or 2 foot square diffusers within a suspended acoustical ceiling because they are a standard ceiling grid, or they fit the standard ceiling grid spaces. They're easy to install and they're inexpensive. There are also similar types available for gypsum wallboard and plaster ceilings. And then you might also see slot air diffusers, and these are used when the appearance of the air distribution system needs to be minimized. Okay, so if we look at the example here, this is an example of the square diffusers. So these basically just pop right into the ceiling grid, and usually they're a perfect 2x2 fit for the ceiling grid size. And then below that is an example of a linear or a slot diffuser. So these are nice because they're a lot more minimal in their appearance, and they kind of integrate just with the look of like lighting systems. So a lot of times designers will do, you see here where we have like a series of linear lights that are running through the ceiling, and then every other row you'll have like a series of diffusers that coordinate with the locations of the lights. Okay, and it's just a cleaner look, and it helps the design look a little bit nicer. So here's a video that covers some HVAC design concepts if you want to learn more about sort of the technical aspects of it and how engineers approach their design of the HVAC systems within buildings. All right, so lastly, we're going to talk about reading HVAC plans. So interior designers should know the basics of reading HVAC plans so they can review drawings to verify existing conditions and coordinate the interior design work with the mechanical engineer's work. Right. This is the same stuff I've been saying this whole time. You just have to understand what you're looking at so that you can effectively talk to the engineer about what needs to happen. You don't need to be the expert, but you need to understand what they are showing on their drawing sets so you can coordinate with them. All right, so here is a partial HVAC plan that was provided within the reading for the week. So what we are looking at here is basically a reflected ceiling plan that has an engineer's HVAC design overlaid on top of it. All right, so this looks pretty complicated, but we're going to break it down so that we can understand what's going on, because it's important for you as an interior designer to understand what you're looking at when you come in, or when you come across one of these plans. Okay, you're going to be seeing these a lot when you get into construction documents and you start putting them together and consulting with engineers and architects. You're going to have to read these, understand what everything on them means. Okay, so let's start out with this little unit right here that has the hatching, the diagonal hatching going through it. You can see we have a leader coming off of it with a note that says AHU1. Okay, AHU1 is going, or I'm sorry, AHU5. AHU, that is going to stand for air handling unit. This is going to be the main unit that's processing all the air. So it's going to be either heating it or cooling it, and then it's going to be distributing that air then through the ductwork. Okay, so you can associate this air handling unit with the furnace that we looked at sort of at the beginning of the lecture. All right, then once that air handling unit processes the air, it pushes it out through the ductwork. So if you look at this ductwork here, the ductwork is indicated by these sort of double lines here, these thick lines, these bold lines, and it's pushing it out through a main duct. The main duct is always going to be the largest, so this entire duct structure is sort of laid out like a tree. You can think of this first duct here as the trunk, and then we have all the branches coming off of it, and they're going to be progressively smaller the further they move away from the main air handling unit in the system. Okay, so if we look at our main duct here, you can see it has dimensions on it of 24 by 16 inches. So these are dimensions that we're going to have if we look at the duct cross section of it. So it's going to be 24 inches wide by 16 inches tall. This one here is going to be 16 by 12, 16 by 14, and then 10 by 8 for this one. All right, so then off of each of these individual ducts, we have what's called flexible ductwork. Okay, so that's indicated here on this table by this sort of squiggly line. It's talking about these lines right here. If we consider a regular duct, these main ones here that we just talked about, those are going to be made out of a metal material, so like steel pan material. Okay, then all of the other ducts coming off of it, these flexible ones, they're going to be made of a flexible material, and they're going to have a smaller diameter than the main ducts that they're branching off of. Okay, and these flexible ducts are then going to diffusers. Okay, so we talked about diffusers a couple slides ago. Those are these. All right, so if you look at what we're seeing right here, we have a square with what looks like an X through it. Okay, Going back here, we have a square with an X through it. So that's a way you can remember it. It basically just looks exactly like a regular square diffuser. What we are seeing here, the squares with the single slash through them, those are indicating our return air grills. So this is where all the air is being sucked back into in order to be redistributed back through the system. So it's going to be pulled back through the return grill, taken back through to the air handler where it can be reprocessed and either reheated or recooled. Okay. We also have linear slot diffusers. So we also just talked about those. Going back here, those are these slot diffusers that you're seeing here. Those are going to be indicated by this rectangle shape. So right here on the plan, we can see we have one linear slot diffuser right here. I'm not seeing any other ones on the plan. I think that may be the only one that's shown, but we can see we have an example of that right here coming off of this duct run right here at the bottom. Okay, so in addition, we have thermostats, right? We talked about thermostats. Those are going to be indicated by this T with the dashed line coming off of it. So every thermostat location where you see a T, that's going to indicate a thermostat on a wall. Okay, so we can see we have one right here outside of this door. We have one inside of this room right here, and then we have one here at the top inside of this space as well. We also have dampers. Okay, so we talked about a fire damper, which we'll cover here in a second, but we have what's known as a manual volume damper. These are locations that you go to individually control the flow of air to a diffuser, okay? This little L shape you're seeing is basically indicating like a little lever. So an air damper, it's basically like a flap. Okay, so if you think back to the fire damper, how that was a series of flaps that closed to prevent fire from moving through, a manual volume damper is basically a flap that you adjust manually with a little lever that's going to block off airflow. So if you decide, hey, there's too much air being pushed through this duct, you can go and you can turn the lever on the damper and it's going to cut off some of the airflow, or you can turn it the other way to open it up and allow more air to go through that duct to the diffuser. Okay. So it's called manual, obviously, because you're manually basically overriding what the system is putting out. Okay. And then lastly, the last one we're going to talk about is the combination fire and smoke damper. So that is exactly what we talked about at the beginning. And that is indicated with this little triangle with the circle. So you can see we have one right here. So if you remember back to when I explained this, when we have a duct that's penetrating through a fire-rated wall assembly, like we're seeing here, I'm assuming this is so this looks like it's a curtain panel system indicated by these three lines. So it looks like there's a mullion and then a pane of glass. I'm assuming directly above that curtain panel, there's going to be a gypsum wallboard wall that has some sort of a fire rating associated with it. So that ductwork is likely penetrating that gypsum wallboard that is above this curtain wall assembly. And where that penetrates by code, we're going to have a damper, okay, that is going to automatically close when there's a fire. When it senses a fire, it's going to shut that damper closed, and it's going to prevent that fire from spreading throughout this ductwork that's in here. All right, so that's indicated right there with that little triangle. Okay, so I know that was a lot to sort of take in and comprehend, but you don't have to be an expert on it. We're basically just going to approach this mechanical stuff as a general broad overview to get you familiarized with the concepts, because that's all you really need. You don't have to know the ins and outs of how they work, but we really just need to be familiar with the terminology and the common systems that you will encounter and have a basic general understanding of what they do and how they function. But again, that's what the engineers are for, to figure out how all this goes together and works. We just have to be able to understand what we are looking at, okay? So that's going to do it. If you have any questions or you're confused about anything, please reach out to me and ask me, and I will help you the best that I can. All right, have a good one.